Okay, so first let's kind of talk about what we're doing today. Yesterday you guys had done the geometric probability, and so then that was pretty straightforward, pretty easy. I think that we just knocked that out pretty quickly, and so that was not a big deal. But today we're going to do a type that's much different and a little bit more complex, and it's called binomial probability. And we're going to look at what this thing called a binomial distribution is. Now, I had on here on the notes to do the expected value and the standard deviation. That is ending up being just a little bit too much for today, so I'm going to not have that part. We're not going to end up doing that. So ultimately, I want you to be able to look at problems and decide if they are a binomial distribution like today or the geometric distributions like yesterday, and then of course compute those things. So this is pages that are not in your packet. I made these just yesterday actually because I didn't really like what was in the packet, and I'm trying to continue to improve this stuff. So this is, hopefully you picked that up over there. If you end up this weekend losing it, or you need a digital copy, it is attached to the lesson plans here. Okay, so I want to give you a heads up on what I want you to think of today as we go through the lesson. So one thing is, of course, when you first read a problem, I want you to decide if it's this geometric or binomial that we're going to be learning about today. Okay? Then, another thing I want you to be able to do is determine what the difference. You'll be explaining in your own words what the difference between geometric and binomial is. And also, we're going to talk about what this binomial distribution is and how it is different from the normal model. Okay, so those are the main things that I want us to be able to figure out today. So we'll go to your packet and your notes. And your notes are that we're going to be working on are on page 40. Okay, so we had started there yesterday with those. On page 40. But what I want to do before we even look at that is talk about that coin flip lab that we had done before. Okay, so do you remember this coin flip lab where we flipped our pennies? What did we do with this lab? We did what with our coins? Flipped our coins how many times? Do you remember? Good, we flipped them 20 times. And so then we were going to see if by the end of all the flips, what that cumulative probability had settled down to. What did we think would happen? That a lot of people would end up close to the 50%, because that was what we expect to happen. Did everybody end up at 50%? No. So some people ended up a little higher than 50%, some people a little lower. Did we have any extremes, real extremes here? I don't think we did. I think the most I had somebody get like 85% in one of my classes, but that was about it. Now, I believe in every single class, after you got your data, I remember that I made a histogram of our data. And so we said, okay, how many of you guys got exactly 10 heads? And how many of you got 9 heads? And so on, and we had those percentages. Okay. And so, did our distribution look somewhat like this? I mean, this isn't perfect either, but wasn't it higher in the center? And then as you got farther away from the center, it went down. Okay, we said it kind of looks like what? The normal model. We said it kind of looks like the normal model. So, now, if I drew a normal model on top of this, because that is one thing we want to do, is talk about how is the normal model different than this. This actually was not the normal model. And so that's about to be one thing that we're going to have a little discussion on. Let's see who's going to tell who what. Let's see. The evens will tell the odds something here in a minute. Okay. but everybody needs to figure out what it is. Now, let's look at these these blue lines versus this red normal curve that I drew. So with the normal model, you know, if I was going to say the proportion of or the probability that I get something less than 6 throws, you know, then it would be this shaded area. But look at the blue area. That is less than the 6 tosses or whatever. It ended up just being those 2 out of the total. So it might be a little bit different probability. So do you see how this binomial distribution is not going to be a perfect estimate, is not going to be approximated perfectly by the normal model? But you see that it is going to kind of be close. You have, you know, it's off, you know, it's not the same here and here. We've got some of those areas that are different. So this binomial can be approximated by the normal, but it won't be the same. Now, here comes the question. I want to know, why does this blue chart of data have, you know, have separate bars here, okay? And why is that a different shape than our beautiful, perfect little curved normal model? Okay, so why is that shape different? Now, keep in mind, I'm not actually interested in the fact that it's unimodal and symmetric. We're going to, say that both of them are pretty unimodal and symmetric. So don't get caught up in that. I'm most interested in this, why I have different bars that even have a blank in between them, and so on. Okay, so let's see if you can answer that. Go. Little discussion. Let's have a little discussion here. Okay, so I've got, these bars do not represent everybody's different trials. These bars represent that, like for example here, 18 people of the sample had 11 heads out of their 20. Okay, that's what that's saying. And so on. And then like here, 5 people out of the sample had, whatever that is, 10, 11, 12, 13, 14 heads out of their 20 trials. Okay, so what's some ideas as to why the blue looks different and would have a little different probabilities than the complete normal model? Any ideas back here? Let's see, who told who? Evens told the odds, so the odds tell me what you guys got going on. So I have gotten that today. I have gotten the thought about how this normal model is kind of, theoretically what would be happening. And then what's in blue is maybe like what actually happened. So also known as the experimental. Okay, so I have gotten that today. I like that. That's a good thought. Not exactly why binomial probability is computed a little differently than normal. But let's keep going. Anybody else have any other ideas of why those distribution or that probability is a little different? I heard some good stuff back there going on. What did y'all say? Yes. There are spaces in between those. Did y'all say something? Good. Yes, there are spaces in between those bars. Did y'all say that? No? Okay. There are spaces because you cannot have part of a flip that gets heads. You are either having 10 heads or 11 heads or 12 heads or 6 heads or 7 heads or whatever out of your 20. So what is happening is this is called discrete data. Okay, and you actually, this word is not a critical vocabulary right now. We'll touch more on it right at the beginning of next semester. It actually has to do with that chapter 16 that we kind of skipped. But are discrete, because we've got finite events happening. You can just have 5 or 6 or 4 or 3 or 2 or 19 or 20. As opposed to the normal model, which is considered more continuous. Continuous, because you can have infinite possibilities. Infinite possibilities. You could have a number like 11.33467. You know, 11.67839, or even smaller. You can have infinite possible outcomes on the normal model, but then there's only finite amounts on this binomial distribution. Okay? So that's the key. So that takes us to our notes on page 40. So when we look at our notes on page 40, and we're talking about why that binomial is a little bit different from that normal model, let's talk about the things that make this binomial. So we're going to remember those conditions with this mnemonic device, bins. So we're going to remember what makes it have a binomial distribution with our bins. So anybody think they know what the B would represent? B. It does have to do with the binomial component. It's binary, which binary really is implying what? 2. Yep. 2 choices. You either have a success or a failure. So if we want to say something is a binomial distribution, follows a binomial distribution, then it's got to be 2 choices, success or failure, heads or tails. You get stopped at the train tracks or you don't get stopped at the train tracks. Okay? So, which reminds me, if you have your train track tally, make sure you fill that out. Okay, very good. So you've got that happening. Now, what do you think that might be? We've talked about it a lot this year. Many times, many chapters. Yep, have a song about it. Independent. So what happens is we know that the trials are independent of each other. So each trial does not affect the outcome of the other trials. Each trial does not affect the other trials. All right. I'm going to go ahead and talk to you about what that is, because we haven't discussed that so much yet. But when we have the number of trials. Number of trials is set. For example, what was the set number of trials that you guys did with our coin flipping lab? 20. Good. If I asked you the proportion of times that you got caught by the train this week, that would be out of 5 days of this week. All right, that you went to on school days. This S component kind of goes hand in hand with the independent. What does the fact that something's independent doing, and that would maybe start with our S? We're having what happen? Same what? Yep. Same probability happening from trial to trial. The fact that the first thing has happened is not changing the probability that the second trial something happens on that. Okay. So those items right there would make something behave like that binomial distribution. Okay? And of course if you had those discrete finite amounts of outcomes. So now let's take a look. Okay, yesterday we had done these geometric distributions. So what could be one statement we said about what our geometric ones were like? What did we do? Perfect. Go until you get your first success, or that success was defined for where it needs to be. So let's talk about how binomial is different from that. Well, first of all, they have a set in. The geometrics don't. You're just going and going and going until you get that first success. Binomial. What you're determining on these is, like, what did we do on our coin flips? We were determining what? At the end, you were telling me your percentage of heads. So how many heads you got out of that set number of trials. So with binomial distributions, it has to do with how many successes are occur amongst the set in number of trials. Okay, so how many successes are occurring? What's the probability that you get such and such a number of successes amongst those amount of trials. So the example that we're going to kind of walk through this with is our one from yesterday, where we went to the store from 5 to 7 p.m. The probability that you're going through the express lane was defined to us to be 0.25, and so now we had already done this one, the probability that the checkout is not used until the 4th. That was our geometric, but let's take a look at today's idea. Find the probability that exactly 2 of the 5 customers use the express checkout. So see, I'm defining how many of a set number of trials. That's what's binomial, that could be computed binomially. So let's do this. How do you think you would mathematically compute that? Saying that we had 2 successes out of the 5. Try that. What math would you come up with for that? Hopefully you were just thinking, okay, I got to have 2 successes and 3 not going through that. Okay, how's that? If you didn't get that, you might have been thinking too hard. It wasn't supposed to be that hard. Okay? All right. So that's good. But what that problem right there is essentially defining is this one situation where you have express checkout lane happening for the 1st and 2nd and not for the 3rd, 4th, and 5th. So you've just described one scenario. If you're standing outside the grocery store and people are coming out, or you have sets of 5s and such, couldn't those 2 people be sprinkled anywhere amongst those 5? Yes. Therein lies the problem. We have different ways in which those 2 can be sprinkled amongst the 5. They could be the 1st and 2nd, or they could be the 1st and 3rd, or they could be the 1st and the 4th, and so on. So at this time, I want you to see if you can't figure out how many different combinations there could be. Now, keep in mind, you actually might have more show up than what I've written out here. So maybe make some more lines. You may or may not use all of them. So do that now. Try to compute as many, see what all the combinations there would be of 5 with 2 successes. Okay, what'd you come up with? How many combinations? At 1st, 2nd, 1st, 3rd, 1st, 4th, 1st, 5th. What would be next? 2nd, 3rd, 2nd, 4th, 2nd, 5th. Then what? 3rd, 4th, 3rd, 5th, 4th, 5th. So how many possible combinations? 10. Now, I will tell you right now, it is purely coincidence that it is 5, the n is 5, and we want 2 successes, and that 5 times 2 is 10. That is not the reason why, okay? So what we would then do is say that the total ways that you can have exactly 2 successes is 10 combinations times these 2 successes and 3 failures. So I want you guys now to put this in your calculator, and you would just do 10 times 0.25 squared times 0.75 squared. I want to see what that number comes out to be. So compute that real quick. Okay, did we get 0.2637, 26.37%? Okay, who told what last? Did odds tell evens last? Odds told evens? Who? What? Evens told odds? Evens told odds? Okay, so now, hey, you know, getting a number in here is just part of the stuff. The math is just, getting a number. But without context and knowledge of what it means, it's worthless. You need to know what that means. So the odds get to tell the evens what 26.37% means. Okay, go. Okay, odds tell the evens, so the evens tell me right here. Who's even? Okay, what do you say? Perfect. 26.37 chance that exactly 2 of the 5 customers you selected are using the express checkout. Perfect. Okay, now, what seems pretty, like a big deal that could get very out of hand very quickly with this process that we just did? Yeah, figuring out all those combinations can get out of hand very quickly. So we're going to talk about how you can do that without having to do all of the combinations. And on the top of the next page, page 41, what we have here is actually the discussion about how you can do combinations. It's not technically required that you have to compute that way. We're going to eventually get a calculator process to do it for us. But I don't want to leave that out. I wanted to just demonstrate for you how that's computed so that it's not just this mysterious number out there floating somewhere. So what happens is this says in combinations of k successes. So I first want to define what n is. N is the number of trials, which in the case of our problem that we're talking about today was how many trials? How many trials did we have? 5 people. Yep, we looked at 5 people. That's 5 trials. And then K is the variable that will represent the number of successes. Okay, so in our case, how many successes did we want? 2. Very good. So I wanted to show you how you would compute 5 combinations of 2. So I have drawn on here the formula of how that gets computed. And so it's hard for you to see up here. I have it drawn very big on this next page. So you could we're going to fill in the numbers together. And you don't have to do that if you don't want, or you can. You could, continue putting it up here and put what that equals and so on. So here's how that works. So this is pronounced in choose K. So we would pronounce this notation in choose K. Notice there is no fraction line. A fraction line in there makes it wrong because then it's turning it into a fraction and not like the process of doing this formula. All right, so our n being 5, we're going to do 5 choose 2 successes. So over here, this first thing I'm going to have is 5 factorial. And so I want to know, does that mean 5? 5! I'm so excited. It's 5. Is that what that means? No. No. What does it mean? What is 5 exclamation point? What is it called? Anybody know? It is factorial, 5 factorial, which is computed 5 times 4 times 3 times 2 times 1. I like these. These are kind of fun. Okay, so 5 times 4 times 3 times 2 times 1. And then, look here on the bottom. K factorial, does it mean K? That means 2 factorial because 2 was our successes, which of course is 2 times 1. How about this here? N minus K, what the heck is that? That's our 5 minus 2, which is 3 factorial. So basically we have the success factorial and the failure factorial. Okay? 3 times 2 times 1. Well, let's compute. 3 times 2 times 1 cancels out. And then I end up with 5 times 4, which is 20, over 2 times 1, which is 2, and that equals 10. It's magic. 10 combinations. And that is not because 2 times 5 was 10. It was because that reduced down to 10. So this is the way you could do any problem. You know, if you had 10, choose 8. Then we could do 10 factorial over 8 factorial times 2 factorial. And that would end up being 10 times 9 over 2. So that would be 45 different combinations. That would not be fun to draw out. And so on. All right. So the moral to that story is that is how you could mathematically compute the combinations. We're eventually going to let our calculator do that for us, even in a different process. Okay, next, what I do need to make sure that you get a firm foundation on today is how to compute binomial probability. This formula that I just highlighted here is the binomial formula on your formula chart. So I want to locate this. This is not something that has to be memorized. It will always be available to you. You will always have a formula chart available to do that. I just want to show you where these things are located. So, for one, do you remember this highlighted pink resource packet I gave you? All right, so you've got that somewhere in your stuff, but I had you pick up a formula chart just to make it easier on you so you didn't have to dig through your backpack. And so here is that formula card you just picked up. Do you see this side that has formula chart there? I'm going to zoom in. And look, on the right-hand side, about midway down, what do you see? This chunk of information here has to do with binomial distribution. Okay, so binomial distribution. And the formula that we are going to be walking through today to make sure that we understand is that one right there. That is the binomial formula. That's how you find the probability of an event on a binomial distribution. Okay, so let's then take a look at that. You've got it again right here. And so what I want to do is fill in this formula. And so you can take this and you could start filling in you can kind of start filling it in right here. I'm going to do it in a bigger form right here, okay? So let's fill this in. So we break it down, and we're not scared of this big funky formula because we always had to show work using that formula. We can fill out this formula and then compute with a shortcut in our calculator. So that's how we're going to do this. First, probability that what we are going for, which in this case is the probability of getting exactly 2, or the number of express checkout customers. K was what in our problem? The number of successes, which our same problem we're dealing with is 2. Good. Okay. Now, what's this next part right here? This mathematically computes what? What did N choose K mathematically compute? The number of combinations. Very good. So the way you write that in our case is 5 choose 2. There is no fraction line. Do not put a fraction line there because then you change it from 5 choose 2, which is 10 combinations, to 5 halves. That's 2 1/2. That's not the same. 5 choose 2. All right. Next, what do you think this P stands for? That is the probability of success. In fact, let's define that here where I have these other little variables. P is the probability of success. Okay? Very good. So in our problem, what was our probability of express checkout? Wasn't it 0.25? Now that probability of success will be different on all problems, whichever problem it is that you're dealing with, okay? We had 0.25. And then look at this K right here. So what am I going to put as the exponent to it? 2. Because we have 0.25 is our success probability, and I want 2 of those to happen. All right. Now, what do you think this thing is? 1 minus P. If P is 0.25, what's 1 minus P? Probability of it not happening. And in our case, what's the probability of you not having an express checkout customer? 0.75. Okay, so you do not, when you write the work out, you don't have to put 1 minus 0.25. You can just put 0.75 there. Okay. So now, what would this be right here? N minus K. Oh, that's the number of failures. So it's the probability of failure to how many failures you want. Now, I wanted to mention something to you real quick. While the AP Statistics formula chart has this failure probability stated as 1 minus P, I will frequently refer to it as a different letter, and it is common in other disciplines to do this as well. Q is a common way to refer to the probability of failure, okay? And so instead of writing it 1 minus P, I'll probably shortcut it to Q. All right, so I want you to notice one thing before we move on and do something else with this. I want you to notice that the number of failures plus the number of successes equals the total number in the total number of trials. That will always be the case. So you know however many failures plus however many successes always has to equal the total number of trials. Okay? So now, guess what, people? This should not be a scary formula to you because you know you have written almost this identical thing already today. You wrote it right here when you told me yourself that there were 2 successes, 3 failures, and then we figured out the combinations. Okay, so the bottom line is I do not want you to be afraid of this binomial formula. It's just identifying how many things and how many combinations. All right? Okay, so this is always the work that has to be shown whenever you do a binomial problem. But I'm going to teach you a shortcut of how to actually use our calculator to compute it, and here it goes. What kind of distribution is this? Binomials. So we're going to do a binomial PDF, okay? And what we're going to put in here is NPK. N stands for, of course, the number of trials. P is probability of success. Now, you could write this right here on your notes. Here's a place for this. Binomial PDF of NPK. Now, some of you have updated calculators, and you have an updated operating system, and it will prompt you for these letters, the number of trials, the probability of success, and the number of successes. But for those of us who have old operating systems and it doesn't prompt us, we need to remember NPK. So I have a silly way to help you remember that. If you can think of narcoleptic prancing kittens, NPK, narcoleptic prancing kittens. Again, this is for those people who don't have the calculator with the operating system to prompt them. Narcoleptic prancing kittens, because, you know, while narcolepsy, yes, is very serious and we don't want to make light of that, can you imagine you get some cute little prancing kittens? And what's narcolepsy? Do you know that? Yeah. So you got the prancing kittens and then they just start falling asleep. I mean, it's actually kind of funny. Have you ever seen fainting goats on YouTube or anything? So they get excited or they get scared and then they just totally stiffen up and fall over, and you know, while serious, it's kind of funny to look at. So again, for those of us who don't have the updated operating system, this little silliness is for you. So we're about to put into our calculator 5 trials, 0.25 is the success, and I want 2 of those. So calculator, here we come. Where do you think binomial PDF is going to be found? Second vars, because it's a type of distribution. Second vars. I'm going to go up because it'll be faster to get to binomial PDF because it's an exact particular amount of successes. Later we'll talk about accumulation. So here we go. 5 trials. 0.25 is the probability. And 2 successes. Whoa. Does that look familiar? Dun, 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 dun. That's what we got the first part of the class when you computed stuff all by hand. There was so much more work. Okay, so that's it. In summary, let me kind of break this down for you. In summary, we identified, you know, this idea of a binomial distribution being made up of these discrete finite items, which is going to be a little bit different computation than continuous normal model. Okay, and then we discussed what those qualities are to make us have that binomial situation, the differences between binomial versus the geometric, and then we had the discussion about, oh, we got these, how many combinations which adds some difficulty level to the math. We went through it, but you really won't ever need that. You just need to know that it's there. And we finally identified exactly how to fill in the formula because that's the work. We don't want to be afraid of that formula. The formula is your friend. It shows you everything. And we shortcut it with the calculator. That's it. So that is how you do probabilities of binomial distributions. So I want to have you take a look at the assignment that you picked up today because this wasn't in your packet. And by the way, you don't have to do what was on there, pages 43 to 46, because this is better. I made this because I like it better. All right. So taking a look at this here, I do not want us to do this expected value and standard deviation component. That's really just too much because I want us to practice about 3 of these before you leave today. So I need to have you take off some problems. Okay, you ready? Here's the ones you're going to take off. Problem 2b, because that's the expected number of successes. Problem 3b. Okay, turn the page. Problem 6, C, E, and F. Problem 6, C, and F. E and F, okay? 7D. 8D. And finally, I want you to notice that 9 and 10 are you explaining in your own words the difference between geometric and binomial, because we had discussed that, and explaining in your own words that idea of the binomial versus the normal model. Okay. All right. So before you leave today, so we have about 10 minutes left, I want you to at least come across, do numbers 1, 2, and 3. I want to throw one caution to you. Look at number 5 real quick. You're going to be finding the probability of exactly 2 or 3 successes. What do you think this OR is going to tell you to do? Add together the binomial of 2 plus the binomial of 3. So you'll have 2 binomial PDFs and then you'll add them together. Okay? All right, get to working.